Moving along with our discussion, let's take a look at a molecule called acetylene, which we encountered previously. That's its common name. Its IUPAC name is ethyne. So this is the simplest alkyne that you could have. So common and IUPAC. Okay, once again, just like we saw with ethylene on the previous page, there's a symmetry plane in the molecule, meaning that the left half of it, if we imagine that that little dashed line that I just drew, imagine that that's a plane that's perpendicular to the page in that area. That means that the left side reflects into the right side exactly, so that's a symmetry plane. So each of the carbons has two areas of electron density around it. Which means that each carbon needs two degenerate hybrid orbitals. So just like we did before, for the sp3 and sp2 arguments, we're going to start with the basis set, which as always is S, P, P, and P. So those are the valence shell orbitals in an unhybridized carbon atom. We're going to pull as many orbitals from the basis set as we need to make hybrid orbitals. So since we need to make two hybrid orbitals, that means we're going to take two orbitals out of the basis set. Again, we always start with S, so we're going to use an S and then one of the P's. We mix those mathematically, and the result is two sp orbitals. And then the remaining p orbitals that we did not use in the hybridization process just come across at the same energy level to be part of the new set of valence orbitals. So this is the set of valence orbitals on an sp hybridized atom. Okay, so we could draw pictures for all of this, but your book is going to have those, or the internet. You can find pictures of that there. So instead, let's just make a list. According to valence bond theory, how are each of the bonds in acetylene being formed? Now, when we make this list, we have to think about both the sigma bonds and the pi bonds. And when we talk about a bond to another chemist, we don't just say sigma. We say CC sigma or CH sigma. In other words, you have to use the atom labels to really specify what bond it is that you're talking about. So when we look at the structure, what we notice is that we have two CH sigma bonds. We have a CC sigma bond. And we have two CC pi bonds. So remember, a triple bond has a sigma component and two pi components. The CH sigma bonds, according to valence bond theory, are formed by the overlap of an s orbital on hydrogen and an sp orbital on carbon. Similarly, the carbon-carbon sigma bond is formed by the overlap of an sp orbital on one of the carbons and an sp orbital on the other carbon. And finally, those two pi bonds between the two carbons are formed just like we saw with ethylene by the overlap in a side-to-side fashion of a p orbital on one of the carbons with a p orbital on the other carbon. And that's true for both of those pi bonds. All right, now let's draw another structure and see how we're doing with this assessment of hybridization and describing bonding using valence bond theory. So here's acetone. Okay, now the first thing we would do if we want to describe the bonding in acetone would be to assess the hybridization of each of the atoms. And the way that you'll do this in most cases is just to count the areas of electron density around the atom that you're interested in, and that's going to tell you what the hybridization is. There's one exception to this, which we'll talk about shortly. Okay, so these carbon atoms over here, the carbons involved in these two methyl groups, they have 4 areas of electron density around them. So each one of them is an sp3 hybrid. The carbonyl carbon has 3 areas of electron density around it. That makes it sp2 hybridized. And the same is true for the oxygen. It has the bonding area, represented by the double bond, and then 2 lone pairs. So it has 3 areas of electron density, which makes it an sp2 hybrid. Okay, so what I'd like you to do is pause the video and make a list, just like we did up above. What are the bonds, what are the types of bonds, including the atom labels, and whether these bonds are sigma or pi. So make a list of all the bonds in acetone, and then see if you can figure out what are the orbitals that are overlapping to form each of those bonds. Now, in addition, here in acetone, we have lone pairs to worry about. So the lone pairs also have to go somewhere. They have to be in an orbital. So see if you can figure out the orbital that they're in. Okay, so having done that, hopefully, what you came up with was the following. There are 6 carbon-hydrogen sigma bonds. Each of them is formed in the same way, or using the same types of orbitals. An S on hydrogen, overlapping with an sp3 on carbon. There are 2 carbon-carbon sigma bonds. They're formed by the overlap of an sp3 orbital on one of the carbons and an sp2 orbital on the carbonyl carbon. There's a carbon-oxygen sigma bond, which is formed by the overlap of an sp2 on carbon and an sp2 on oxygen. There's a carbon-oxygen pi bond. The pi bond is formed by overlapping a p orbital on the carbon with a p orbital on the oxygen. And finally, oxygen's lone pairs. Where are those? Okay, well, let's assess what's going on with the oxygen. The oxygen, remember, is sp2 hybridized. So as such, it has 3 sp2 orbitals and a p orbital. The p orbital is perpendicular to the plane of the page. The sp2 orbitals that I just drew in are all on the same plane. That's the plane of the paper. One of the sp2 orbitals is being used to form the sigma bond to the carbon, to the carbonyl carbon. That leaves 2 other sp2 orbitals, and that's where the lone pairs are. So the lone pairs here are both in sp2 orbitals. Okay, so that's been a lot of information. So let's summarize. And once we summarize, you can go back and if any of the arguments were confusing, having the bottom line, having the spoiler alert, if you will, you can go back and review the ideas and say, okay, that's where they came up with it, and now I understand a little better. Or ask them questions. Okay, so valence bond theory. If we're invoking valence bond theory to describe bonding in a molecule, what we want to keep in mind is the following. Hydrogen always uses an s orbital. So it's never going to be anything else. It's always an s that it's going to use to form its bonds. Pi bonds, as we've seen, are always going to be formed by overlapping p orbitals. So if I ask you how a pi bond is formed, the answer is always going to be p orbitals. So pi bonds are always formed by overlapping p orbitals, one on each of the atoms involved in the pi bond, of course. And this is done, and you probably heard me mention this, in a side-to-side fashion. Side to side means the orbitals are aligned this way, and so the overlap occurs in the regions that I just colored in. An end-to-end overlap would look like this. Okay? but a pi bond is side-to-side overlap of the p orbitals. And finally, and this is probably one of the most useful things that you'll get out of this summary, the hybrid orbitals. Hybrid orbitals are used to form sigma bonds and to hold lone pairs. So if you see a lone pair on an atom, it's most likely going to be in a hybrid orbital. Okay, now for our new sets of hybrid orbitals, because this is what we're going to be working with, what are the valence orbitals for atoms that have each of these hybridization states? Okay, so we talked about this when we developed the argument for how each of these hybrid states were constructed. But let's just summarize it here. If you're an sp3 hybridized atom, then the orbitals that make up your valence shell are 4 sp3 hybrid orbitals. You no longer have any unhybridized s or p orbitals. Now you just have the sp3s. If you're an sp2 hybridized atom, then your valence set now consists of 3 sp2 orbitals and a p orbital. And if you're an sp hybrid, your valence set consists of 2 sps and 2 ps. Counting the areas of electron density around a particular atom in order to come up with its hybridization state is going to work for you 95% of the time. But the other 5% of the time, there's an exception that you have to be mindful of. So it says here, exceptions to our simple hybridization model exist, but we really just care about one. And that has to do with resonance. So now we're going to take a step back, and now that we know some things about hybrid orbitals and orbitals in general, we're going to think about resonance again. Okay, now here's a structure of an ester. So we're going to start from there. And remember that with an ester, the pattern for resonance that we recognize is that we have a lone pair next to a double bond. And you'll remember that when we have that kind of a picture, that the resonance argument we can invoke involves these arrows. So that gives us this minor contributor, like so. And remember that the place that we got to that from involved the allyl anion. So a lone pair next to a double bond means you can do this kind of thing. Okay, so by drawing these curved arrows, what we're showing is that electrons are delocalizing. So I'm going to use a different color here. Is that electrons are delocalizing across these 3 atoms in each of these cases. For that to happen, we have to have what's called a pi system. Okay, so let's look at the ester structure again, the original ester structure. Let's take a look at the ester oxygen. Remember, the ester oxygen is the one that's not the carbonyl oxygen. Okay, so if we count the areas of electron density around the ester oxygen, we see that there are 4. So 4 areas of electron density, which means that it looks like it's sp3 hybridized. However, the fact that we can delocalize electrons by showing the resonance arrows the way that we do means that there has to be what's called a pi system involved in this. So let's go down to the bottom of the page and then we'll jump back up. So let's look at an allyl cation. That structure is shown to the left. Now with an allyl cation, it's very easy to see that each of the carbon atoms is sp2 hybridized. And so each of those carbon atoms has a trigonal planar geometry around it. So all of the bonds that are shown in that picture are in the same plane. Okay, so remember that with an sp2 center, you have a p orbital that's left over after the hybridization argument, and it's going to be perpendicular to the plane. So the first photograph shows the allyl cation just the way it's drawn to the left. So all of those black sticks are the bonds that are in the plane, the bonds between the carbons and the bonds to the hydrogens. And so you can see in the model that there's a trigonal planar geometry around each of those carbon atoms. So these are all 120-degree bond angles, like so. And same for the other two carbons. Now, if we tilt the model on its side, or if we move, the model doesn't want to move, but we move, and we look at it from the side, what you see is the picture on the right. Now, these red sticks, I'm going to ask you to use your imagination. Each of these red sticks, which in the original intended use in the model kit is as a bond, is a p orbital or a lobe of a p orbital. So you have one here, you have one here, and you have one here. Okay, now notice that all of those p orbitals are parallel to each other. When they're parallel to each other, that permits them to overlap with each other to the maximum extent possible. Okay, so now let's go back up to these pictures up here. If we're thinking about resonance, like I said earlier, we have to have a pi system, because what resonance is showing is a delocalization of electron density in the following fashion. It involves a set of p orbitals that are all parallel to each other and all on adjacent or consecutive atoms, such that electrons can be shared among that entire set of p orbitals. This is what's known as a pi system. The fact that the p orbitals are parallel to one another is what enables the best overlap to occur. The better the overlap, the more efficient the delocalization of the electrons. So that means that the electrons are really getting spread out, because it's possible to do that because the overlap between the participating orbitals is very efficient. So that's really what's going on here. Okay, so let's look at this diagram. So this oxygen here is the carbonyl oxygen. This is the carbonyl carbon. And this is the ester oxygen. Now our initial thought, our initial suspicion, to go back up to the resonance structure or the structure of the ester, upper left, was that the ester oxygen in the major resonance contributor has 4 areas of electron density, which makes it look sp3. So let's imagine that it is sp3. And then let's go down to this picture right here. The overlap between an sp3 orbital and a p orbital is not going to be as efficient as the overlap between a p orbital and another p orbital. So you have less efficient overlap there than you would if that were a p orbital. But to have a p orbital on that ester oxygen, it would have to be sp2 hybridized. And so that's where the exception comes into play. The ester oxygen looks like it's sp3 hybridized because we counted 4 areas of electron density. But because it's involved in a resonance argument, it has to be sp2 hybridized, because only an sp2, or for that matter, an sp hybrid atom, is going to have a leftover p orbital that can participate in a pi system. This is going to be true in all cases where you have a lone pair next to a double or a triple bond. So the ester oxygen, although it looks like sp3, is actually sp2, and that's because of the resonance argument. So that's the exception that you have to be on the lookout for. The exception involves where we have a lone pair on an atom next to a double or triple bond. The atom with the lone pair has to have a p orbital, otherwise we couldn't invoke the idea of resonance. And because it has to have a p orbital, so that that can participate in the pi system, it has to be sp or sp2 hybridized. Now, the vast majority of the cases that you're going to see will be sp2 hybridized. So that's what you have to look out for. Okay, so the actual best label for the hybridization of the ester oxygen would be sp2. Okay, so anytime you have a lone pair next to a double bond, that's going to be the case. So let's look at the next page. Let's just, these are just a couple of examples of pi systems. So you've got two, one of them turned out looking a little better than the other one, which is kind of strange looking, but p orbitals, one on each of the atoms. In this first structure, these are all sp2 hybrid carbon atoms. And as such, each one of them has 3 sp2 orbitals and a p orbital. The p orbitals are all perpendicular to the plane of this molecule, and as such, they're all parallel to each other, which permits the most efficient delocalization of electron density. Benzene is another example of a molecule that has a pi system. Each of the carbons in benzene has an unhybridized p orbital. Now, just to make sure that we're extending this correctly, it's not just esters where you would invoke this argument. Anything that's a carboxylic acid or another kind of carboxylic acid derivative is going to have the same argument. So it's easy to see in the major resonance contributor, for example, of an amide, that the carbonyl oxygen is sp2 hybridized, the carbonyl carbon is sp2 hybridized, but the amide nitrogen, because it has 4 areas of electron density around it, appears to be sp3 hybridized. However, we know that because these electrons on the nitrogen are participating in a delocalization argument, that nitrogen has to have a p orbital on it. As such, the best label for its hybridization is going to be sp2, not sp3.